Hello. Now, today we're going to continue our work in algebra and we're going to be looking at the graphs of cubic functions, and we're also going to touch on the graphs of higher order functions, so higher degree polynomials like x to the power of 4 or x to the power of 5. But our main focus is on cubic functions. Now, a cubic function looks like this. A positive one is going to start rising up from negative y's, I should say, up to the top of a hill. This is called the maximum point. It's going to drop down into a valley. This is called the minimum point, and then it's going to start rising again. This is in contrast to our x squared type functions that would look like a smiley face or would look like a frowny face. So this is what our cubics look like in general. So in the same way, in the back of our minds with our positive x squareds or negative x squareds, we have a picture as to what they roughly look like. This is what it roughly looks like to have a positive cubic function. And the way that I remember, which way around, so this is what a negative cubic function looks like. It starts off with positive y's and ends up with x being negative. The way that I remember which way around these goes is to remember that the highest power is going to become the most important as x gets bigger. So if we think of 10 cubed, it's going to be 1,000, as opposed to 10 squared, which would only be 100. So as x gets bigger, the value that really matters for determining the y coordinate is going to be the cubed part. So if the cubed part is positive, we're going to end up with positive y values as x gets bigger. And likewise, if x cubed is negative, if the coefficient is negative here, it almost doesn't matter. As x gets bigger, this stuff becomes very unimportant. The fact that this is negative, something cubed is negative, ends up meaning that we end up with y values that are negative as x gets bigger and bigger, and the cubed becomes really the only important part of our function. So that's how we can remember which way around these goes. But the general shape of our rising up to a hill, dropping down to a valley, and then rising up again for our positive cubic is the main thing we need to have in the back of our minds, just like our smiley face and frowny face. Now, these tops of hills and bottoms of valleys are going to be important in sixth year. We're going to come back to them when we're doing differentiation, when we're doing calculus. Because if I draw a very quick crude sketch here, the slope of my cubic at this point is going to be 0. So here I have a positive slope, it's rising. Up here I have a slope of 0. My slope is effectively flat at the top of the hill for a moment. I drop down and have a negative slope. And then at the bottom of my valley, I change direction again. And for a moment, my slope is flat. My bottom of my valley is going to be have a slope of 0. I'm not rising or falling for a moment, and then I'm going to have a positive slope after that. Now, I'm only touching on that now so that when we come back to it in sixth year, you have a little bit of a feel for what we're talking about when we're looking for the maximum, the top of the hill, and the minimum, the bottom of the valley values for a cubic. And in terms of sketching these things, like we're going to want to be able to do at the end of today, it's also relevant and to be able to find the maximum and minimum points, which you'll be able to do when we've done calculus, when we've done differentiation. But getting into today's work, what we're going to do is look at a few examples of different cubic functions and see how we could draw how we could figure out what their equations were based on the pictures of them, based on the sketches of them. So the brightness of the screen is going to change now. So what I've got here is this function. In the question, you would not be told this equation, or most times you wouldn't be told this equation because you're supposed to be finding it. So if we were given this picture and we wanted to find this equation, if we wanted to find this cubic equation, what could we do? Well, what information am I given in this question? If I'm given this picture, it tells me a lot about the function. I know that it has a root at x is equal to 0, at x is equal to 1, and at x is equal to 3. And I know that the point 2 minus 2 is on my line, is on the curve. Or I could say that at 2 minus 2 is contained on the curve. So those are the pieces of information I can get from my picture. The roots Where it would cross the y-axis is often a point that we're going to look for, but another point on our function. So if we want to sketch something, or if we want to find out its equation, we're always going to be looking for the roots and another point, usually the y-intercept, but it can be any point on our function. So the roots and another point, usually the y-intercept, is what's going to allow us to form our cubic or any other function that they ask us to draw. So let's get into this. We know what our roots are and we know the point 2 minus 2. So I'm going to switch back to writing and I'm going to say I know that x is equal to 0 is a root, x is equal to 1 is a root, and x is equal to 3 is a root, and I know that the point 2 minus 2 is on my line. So x, when x is 2, y is minus 2 is a point on my function. And that is all the information I need to find this equation. I know that if I have the roots, I can rearrange these roots in order to get the factors. I just set my roots equal to, I want to rearrange this so that my roots are now equal to 0. So x is a factor, x minus 1 is a factor, x minus 3 is a factor. So I know from my work before that y is going to be equal to some multiple of my factors multiplied together. So x multiplied by x minus 1 multiplied by x minus 3. I'm just multiplying out these brackets here. And when I do that, we all know how to multiply out brackets. So when we have done that multiplying out, we will get x cubed minus 4x squared plus 3x. And now I need to find this value of k. But I know that 2 minus 2 is a point on my equation. So I can sub in x is 2, y is minus 2, and find the value of k, just like we've done before. So I sub that in. And when I simplify this bracket, I'm going to get k is minus 2. So minus 2 is equal to minus 2k. Therefore, k is going to be equal to 1. That means that the equation I am looking for is going to be 1 multiplied by x cubed minus 4x squared plus 3x is going to be equal to x cubed minus 4x squared plus 3x. That's my cubic equation that I'm looking for. Now, one might wonder why I bother with the k if it's just going to be 1. So what we're going to do is show how we can have the same roots. We're going to switch back to GeoGebra for a moment. I'm going to multiply this function by 2. Now what's happened? My roots have remained identical. I still have x is 0, x is 1, and x is equal to 3 as my roots, but I can now see that the point on my function has gone to 2 minus 4 because I multiplied this by 2. So my roots are identical. Multiplying by a constant has not changed my roots, but I now have a different point on my function because it has effectively been stretched. Every single y output has been multiplied by 2, so it's been pulled out away from the roots. All of my y outputs are now double the distance on my y-axis. So I can now double check my answer. I know my roots are the same. Switching back, I know that I still am going to multiply at the same root, so I'll get to the same point here. Y would be equal to k multiplied by x cubed minus 4x squared plus 3x. But now my intercept, one of my points, I should say, one of my points on my line is 2, -4. So if I set that in, I get -4 is equal to k on 2 cubed minus 4 on 2 squared plus 3 by 2. When I simplify that down, I get k is equal to -2 is equal to -2k. So I end up with k is equal to -4 divided by -2 is equal to 2. So my y is equal to 2 on x cubed minus 4x squared plus 3x. This function then, the one that I had multiplied by 2, ends up being 2x cubed minus 8x squared plus 6x. So this is why the k is important, because I need to double check using my extra point, using either the y-intercept or another point on my function. I need to be able to check what my constant is going to be, because changing back to GeoGebra, they could very easily give you a situation like this where they had doubled what you would get from just multiplying out the factors. So we need this third point. Now, if they don't give us a point, or if they don't give us a y-intercept, then we just multiply out the factors and we don't worry about it. But if we have a third point, if we have an extra point, I should say, on the curve, or if we have a y-intercept that isn't also a root, then we can use that to figure out what our constant is, what our factors have been multiplied by. So that is the introduction to our cubic.